from NIST, so nearby, and he'll tell us a little bit about some studies of superlattices of bismuth ferrite.
Thank you very much. Hi, everybody. Thanks for the talk. I really appreciate it. So I'm Colin Heikus. I'm currently at the NCNR doing neutron scattering. And so this is a collaboration we've had going now for a while on kind of the coupling between magnetic ordering and polarization domain structures in bismuth ferrite and using superlattice engineering to attempt to alter this. So, come on. So I think we're all pretty familiar with bismuth ferrite at this point. A lot of the interest in bismuth ferrite as a multiferroic really stems from the idea of coupling the polarization state and the very high polarization state you get in bismuth ferrite, and coupling that to magnetic switching, and being able to control magnetism in bismuth ferrite through an exchange bias with the flipping the polarization state with a field. And so bismuth ferrite's also exceedingly interesting due to all the various domain wall effects you get. You can have these charged domain walls, conducting domain walls, a whole zoo of various possibilities given the rhombohedral or pseudo-rhombohedral structure that bismuth ferrite forms in thin film states. So also, these domain walls not only are conducting, they can also be photoconducting, and there's lots of work, using bismuth ferrite as or attempt to use bismuth ferrite as kind of a novel photovoltaic where you get kind of enhanced photocurrents due to the internal fields, or that's the idea. And then also, bismuth ferrite has a couple different interesting kind of ground state ferroelectric structure-based interests where you kind of tune through a morphotropic phase boundary, both with strain, where you can kind of tune between this tetragonal phase and this rhombohedral phase and mix states it and get this enhanced piezoelectricity. But also, you can do this with pressure and chemical pressure and all sorts of things. And then also, with chemical doping, you could tune through a second morphotropic phase boundary, where you're going from this standard R3C-like ferroelectric rhombohedral bismuth ferrite state. You dope in any rare earth, in this case it's samarium. You enter this intermediate regime where you get this 4-by ordering, which is like a lead zirconate-like structure, so antiferroelectric-like structure. And then you get high enough and you transition into a paraelectric orthorhombic structure, similar to lanthanum ferrite or other rare earth ferrites. Now, the important thing here for what I'm going to talk about is, I'm going to mention magnetism a bunch because I do neutron scattering. And in this case, through this whole phase, as far as we know, for this region, it's a G-type antiferromagnet, where in thin film case, you kill the cycloid for most strain states. And in this case, it's just also a normal G-type. But the tilting patterns are different going from the rhombohedral state to the orthorhombic state. And so the question is, so not using strain and not using chemistry, can we somehow tune these ground states, these ground polarization states, and perhaps couple to the magnetic states using interfacial or boundary condition engineering? And so what we've done is we've grown a bunch of superlattices, and what we're doing is we're actually growing bismuth ferrite and lanthanum-doped bismuth ferrite. So in this case, the bismuth ferrite should be in the rhombohedral ferroelectric state, and the lanthanum ferrite should be well into the paraelectric state. So you kind of have this frustration of a polarization building up through the bismuth ferrite, as well as a paraelectric state in the orthorhombic system. And so we've grown a bunch of these. MBE is very nice for this because we can grow the bismuth ferrite in an absorption-controlled regime where the thickness is controlled by only one flux instead of having to balance flux to get correct stoichiometry. So in this case, we can grow absorption-controlled both for bismuth ferrite and for 40 to 70% lanthanum-doped bismuth ferrite. So this is well into this regime where we're not anywhere close to this morphotropic phase boundary. Of various characterization techniques, so diffraction, reflectometry, and X-rays, various TEM. I'm going to show a bunch of TEM data. EELs, STEM, all indicate good growth, high-quality films. And as I said, this chemistry is important. All of our lanthanum-doped layers are well within this paraelectric state. And so you get a characteristic, benchtop X-ray here where even though we only have, our only contrast here is just the lanthanum on the bismuth site, right? That's the only Z contrast we have. We still get nice, sharp superlattice reflections. This is for a 10-10 superlattice, 20 repeats. We get these nice, superlattice reflections throughout the whole series, and they index correctly. So here's a nice TM image of one of these films. And so you can see, once again, high quality, but we have clear, nice, clean interfaces throughout the whole film. And so then, what happens when we actually go and we image the displacements of the various atoms to try to map out the polarization state? And so what you see is that you start to see this interesting up, up, down, down pattern, which is very similar, at first glance this is very similar to the lead zirconate-like antiferroelectric state. And so, so we get multiple different domains of this, and these domains can coexist with, this is a ferroelectric displacement pattern. And so this is a very similar state, or by TEM so far, this looks like a very similar state to what we see at the morphotropic phase boundary. But in this case, we don't have morphotropic phase boundary composition in the bismuth ferrite. We have pure bismuth ferrite interface, and we have regions where it's just ferroelectric. But for the most part, we have these nice full field for this particular film. And so this is a 14 repeat film. So you might immediately ask, okay, so you have lanthanum diffusion, and that's what's going on here. You have some sort of lanthanum diffusion through the film where you're actually at the morphotropic phase boundary somewhere, and that's triggering this. And so Lena's group did some nice EELS mapping from these films. And what we see here is that we have nice, no significant lanthanum interdiffusion. And I think the error bar on this is like less than 2% lanthanum possible in the film through these EELS images. And so that puts us, both the bismuth ferrite is well on the rhombohedral side of the morphotropic phase boundary, and the lanthanum doped bismuth ferrite is well on the orthorhombic side of the phase diagram. And yet we're seeing something consistent with this quarter spot ordering that is this lead zirconate-like phase. So we had some collaborators do some calculations to see if this is a stable antiferroelectric phase. And so yeah, they stabilize the lead zirconate phase in bismuth ferrite, but they also stabilize 3 other possible structures of this that corresponds to this up, up, down, down modulation of these atoms here. And so at this point, we know that we have this. All these are the antipolar phases. So we know we have something where we have this pattern in the TEM, but it could be any of these phases, and they're still working to kind of figure out what the lowest energy phase is and determine what's going on here and why we're driving this. But clearly we have these other non-R3C-like structures nearby in energy space, and just by coupling to the, making superlattices here, we've stabilized a new ground state. So not all of our, so the other thing is this PBZ-like structure can't be stabilized with strain alone. And so you can see that here where you've got the R3C phase is stable over all strain states here that they calculate. And that's kind of consistent with the fact that nobody's really seen this just making monophase BFO on various substrates. And a lot of work has been done with this for the tetragonal and the morphotropic phase boundary there. So that's not the only phase we see in these films. We actually see a huge zoo of possible ferroelectric or polar systems, and they can coexist. So clearly, this interface engineering is right on the edge of some instability with the polar ordering that you get. And so here's an example where we have these nice 180 degree, 190 degree domain walls throughout a whole film. And so here's a region where we have this orthorhombic antiferroelectric stripe phase. And then here's a system where we have this mixed phase region where we can go from, and this is actually, there's a couple different other antiferroelectric phases I don't think I'm going to get to for time, but we also see other other modulations of these sites that give us other antipolar phases. And they can all coexist in a single film. And we're still trying to figure out what the control parameter is to isolate one versus the other. But that's ongoing work. And also, so that you can ask the question, okay, so we have these polar distortions, and unfortunately, we can't grow these films with electrodes where we can switch them easily. Or we haven't been able to yet. So next best thing, we have some PFM showing kind of the topography here, and then you got the amplitude and phase images here showing that we do have regions of piezo response, showing that this is a plane view, right, of coexistence of regions through the film with both ferroelectric ordering and non-ferroelectric ordering. And so this corresponds, right, like looking down through the film to regions of antipolar and potentially ferroelectric regions. So I said I was going to talk about magnetism. And that's a real question here. So we have some novel polar ordering, and we know bismuth ferrite has a strong coupling between the ferroelectric state and the polar ordering and magnetism. And you can, that's the whole electronic control of magnetism thing. So as a neutron scatterer, we uniquely are capable of coupling to the magnetic moments in a film. And in particular, we're going to use a technique called polarized neutron reflectometry here. And I think for this audience, it's good for me to explain what's actually going on here so you can get a sense of what we're doing. So in this case, we have neutrons that are sourced from our reactor, and they come down in a reflection geometry, and they reflect off the surface and go to our detector. And we get some profile similar to X-ray reflectometry, where this structure is due to Bragg scattering, as well as of the thickness of the film and the contrast of the scattering density of the substrate with the film. And you get a sense of roughness, and you get a sense of film thickness out of the Q spacing of these wiggles, as well as how damp they are, how underdamped they are. So we can also do this with a polarized neutron beam, now where the neutrons couple differently to opposite directions of magnetization over the length, the correlation length of our neutron. And so in this case now, for a magnetic sample that has a moment here, we get two different scattering profiles for the opposite, up, polarized. So neutrons that are polarized up that come out up, and neutrons that are polarized down that come out down. And we can also do the cross terms too, and that gives us kind of a orthogonal component of the magnetization. So we get some data set, and typically we think about this in terms of not intensity, but rather a differential intensity normalized by the sum of the intensities, so like a spin asymmetry term. So we take this data, we then model it with what we know of the structure from various X-ray or TEM techniques, and from doing the growth ourselves, we know what we think we have. And we can compare this to reflectometry consistently and feed this back into a model until we get something that converges and generates a nuclear profile. So this is the nuclear contrast, and a magnetic profile and the magnetic contrast, and this is an incoherent thing here. And we also can back out the direction of the magnetization with respect to the field we're applying. So in this case, we're actually applying a magnetic field to orient the moment, so we don't have to deal with domain effects. So what you get is you get depth resolved magnetic and nuclear profile, and you get angstrom resolution here. So this is one of our films. So this is a 3-repeat film now. And I should note that the TEM of this film shows actually that we get an anti-ferroelectric pattern throughout the entire film, which maybe is unsurprising because there should be some crossover regime where they're coupled. And this is actually a composition that is in the morphotropic phase boundary, despite still seeing clear segregation where the bismuth ferrite is bismuth ferrite and the length of bismuth ferrite is bismuth. But if you average over the whole system, you're in the morphotropic phase boundary, which is kind of what's always going to happen for these 40% lanthanum films with 50-50 superlattice ordering. So in this case, this looks really impressive because this splitting should all come from magnetization, but I should warn you that terbium scandate has a really large anisotropic paramagnetism, and we couple to that too. So a large portion of this spin asymmetry is coming from the magnetization in our substrate, but because we have depth profiling, the Q dependence and where we deviate from Q gives us some the ability to tell apart the magnetization in the substrate from the magnetization in the film as we fit our model iteratively. And so this fit, so you can see my fit here to this data. This fit corresponds to a profile where, in this case, I know I have a superlattice, but I've only measured out in Q far enough where I wouldn't actually see the superlattice ordering for such a tight. So I'm actually simulating this with a model, with an alloy model where I'm assuming just a incoherent mixture of lanthanum and bismuth ferrite at the correct composition. And so, given this model, I have some substrate nuclear profile, an alloy, and then some roughness of the surface. And the same thing I have. This is a nuclear roughness, as opposed, that the nuclear roughness can be different from the roughness you measure with X-ray, just because of the coherence length of the neutrons and how sensitive we are. So then I have my magnetic profile, and so I see a really high magnetization in my substrate. But then my fits always converge to something that looks like a uniform magnetization. And in this case, I'm not allowing the magnetization to oscillate with the periodicity of the superlattice, just out of interest of getting a nicely fitting model. But if you look, the parts where I'm missing the asymmetry are in this Q range around 0.05. And this Q range is interesting because it corresponds to like 1/4 of the superlattice repeat. So something's going on here where we have what looks like a uniform, or some non-trivial magnetization in our film that's about an order of magnitude higher than what's expected for bismuth ferrite. And so our fit corresponds to when we convert the scattering density to like almost a half MUB per iron site. And that's assuming a uniform magnetization. So if it's only in the bismuth ferrite, if it's only in the lanthanum, if it's only at the interfaces, it's actually a higher magnetization. Now I should note that this is under a 3 Tesla field. So this does not survive to relaxing the field. So this is not a ferromagnetism that we're seeing here. This is some sort of anisotropic paramagnetism or free spins in the film. And we expect this might have some sort of interfacial effect. because we don't see this for films that have fewer interfaces, basically, that have a lower interface density. And so we've also done elastic scattering, just to note that our elastic scattering is consistent with half-half-half G-type ordering with no cycloid. And with that, I'm going to leave at my conclusions. So we've grown these superlattices, and we have this novel polarization state. We're still trying to figure out what the control mechanism is for this, but it certainly seems that when you start to make superlattices of bismuth ferrite with effectively no strain here, because we're growing on a system where we have less than 0.5% strain from the substrate, and then we have the lanthanum and bismuth are roughly the same size, so we're not really getting any sort of superlattice buildup of strain in the system. We have an apparent paramagnetization at 3 Tesla in these systems at 5K. And we see a clear half reflection with no evidence of cycloid. Now, I should note that we've also tried field dependence of the elastic scattering. And so what we see is a slight field dependence of the scattering intensity at this half peak, but we're still trying to run this down and make sure that this is real. And with that, I'll thank you and take questions.
Okay, we have time for some questions.
Actually, you could resolve the problem with the magnetism if you would use...
I'm sorry, I can't hear you.
You could resolve the problem with the magnetism if you would use μSR, because this is depth dependent, and you can really trigger that. Yeah,
so we're looking into that for this system as well. Nominally, the reflectometry should have a very similar. The μSR will tell us whether it's the film, but you don't really have the resolution with the soft μSR to tell the difference between. You can do kind of 15 to 20 nanometer steps.
So you can even do it on the surface.
You can do just on, yes, you can do just on the surface, but as you start going in the depth of MUSR, you start to lose spatial resolution as you get. So you can tell at the top versus the bottom, but for a film this thick, you start to, we're talking about a 70 nanometer thick film. And so as you start to get an energy broadening, right, of the MUSR.
That's new to me, actually. I know that it's very precise and you can detect any magnetism at any depth in the
Yeah, it's very sensitive to low magnetism, but it's the depth profiling with soft MUSR is very dependent upon just the energy. You pick where in the film you deposit the muons, and so that the thickness band of where the muons are and for your resolution spatially is limited by the energy you have to use to deposit them. So as you progress through the film into the substrate, you broaden out your muon profile significantly.
Nevertheless, I think it's the most precise method.
Yeah, no, absolutely. We're definitely thinking about that.
Any other questions? All right, let's thank our speaker one more time.